Welcome back, Chemistry 30. This is the second part of the balancing with redox reactions. So I left you with this, and you're supposed to write down the oxidation numbers of each element and see what the gain or loss was for each one, and then from there we could balance the equations. So what you should have ended up with is something like this. So the red parts here, so +1, -1, +1, +5, -2, etc., etc. So you would have done this. Keeping track of the total charges on the bottom helps you figure out what the individual ones are. Okay, so then going from left to right, H does not change. It's this +1 on the left and right. Cl though, over here, Cl goes from -1 to +1. And that's primarily because oxygen has a higher electronegativity than chlorine, so oxygen's oxidation number will be -2. Hydrogen +1, that means chloride will be +1 as well. So we're going from -1 to +1, so of course oxidation is happening there. And to go from -1 to +1, that's adding 2, +2. Okay. Nitrogen went from +5 to +2, so it's getting more negative, so it obviously was reduced. And to go from 5 to 2, that's a difference of -3. So we have -3, +2. Of course, we have to make those equal. That's part of the rules with balancing by redox. So if you take a look back here, what we've done so far is assigned oxidation numbers, identify the oxidized and reduced items, determine the oxidation numbers, make the change. We're about to do this now. Make the change in oxidation numbers equal by adjusting the coefficients, and then use old ways of, or conventional ways of balancing the equation. So 2 and 3 both go into 6, so multiply this by 2, multiply this by 3. So those are the changes that we will in fact be doing. So we need to have 3 chlorides, 2 nitrogens. So to do that, 3 chlorides, 2 nitrogens, 2 nitrogens, and I think it is balanced. 3 Cl's, 3 Cl's. 3 plus 2 is 5 H's, 3 plus 2 is 5 H's, 6 O's, 3, 4, 5, 6. So there we go. The next one looks something like this. So maybe I'll pause the video here. You assign oxidation numbers, figure out which element is oxidized, which is reduced, figure out the change in oxidation number, and use a coefficient here to make it equal, and then see if you can balance it from there. Okay, so pause the video and try that out. Okay, if you had time to do that, assigning oxidation numbers, you should have got this. So -1, +4, or 0, -1, +2, -1, +3. So if you look at tin, going from +4 to +2, it got more negative, so it's being reduced. That change that happened from +4 to +2 is -2. Iron went from 0 to +3, so it got more positive. That's oxidation. And the change that happened to go from 0 to 3, that's +3. And again, lowest common multiple is 6, so multiply by 3, multiply by 2. So I need to have 3 SNs, 2 irons. So we'll just apply that technique. 3 SNs, 2 irons, and I think everything else works out. If I look here, 3 times 4 is 12 chlorines, 3 times 2 is 6, 2 times 3 is 6, so 12 chlorines on the right as well. Last one we'll look at, this one. So I'll pause the video and you write down the oxidation numbers on top, figure out what's oxidized, what's reduced, figure out the net change, and then try to balance it. So pause the video now. Okay, if you had an opportunity to do that, this is what you would have found out. So -3 + 1, oxygen is more electronegative than nitrogen, so -2 + 4, etc., etc. Nitrogen goes from -3 to 0, so it's getting more positive. It's losing electrons, so that's oxidation, and that difference from -3 to 0 is +3. And this nitrogen changes as well, so we could have that happen, folks. One nitrogen goes to this nitrogen, another one goes to this one, +4 to 0, so it's getting more negative, so it's reduced, so it's -4. So 3 and -4 both go into 12, so I'm going to have 4 here and a 3 here. I just wrote this 4 on the right because it get cluttered over there. So how you handle that? Now, we're all going to this nitrogen here. So 4, and we need to have 4 nitrogens here. Don't worry about this one yet. I need to have 3 nitrogens here, so I did that. So that's going to give me 4 plus 3, that's a total of 7 nitrogens. Now what multiplied by 2 gives you 7? 3.5. Okay, well, let's leave it like that for now. Balancing the H's, here I have 12. So to get 12 here, I need to have a 6 in front of there. That's going to give me 6 O's. Hey, and I have 6 O's here. Now usually we don't leave things in terms of a decimal or a fraction, so of course we would double everything there and we get that. So this is the conventional way of balancing that we would have used. Double everything to get rid of the fraction or the decimal. 3.5 doubled is 7, 6 doubled is 12. All right, so that's kind of the scheme as to how you balance redox reactions. Okay, if you look at the next part here, the last part, balancing net ionic redox equations. This one's a little more tricky, so we'll spend a little more time with that one. Sometimes chemists prefer to express redox reactions in simplest possible terms as an equation showing just the oxidation and reduction processes only. So if we have this equation, copper plus nitric acid yields copper nitrate, nitrogen dioxide, and water, we can see there's 2 substances that are aqueous here. So note it takes place in aqueous solution, which is a strong acid. It'll be ionized. Likewise, copper 2 nitrate will be dissociated. So those things that are in aqueous solution, they actually exist as 4H pluses, 4 NO3s. Copper 2 plus and 2 nitrates. Okay, you can see that there are 4 nitrate ions on the left and 2 nitrate ions on the right. So only 2 of them undergo a change to form NO2. So that means the other nitrate ions are spectator ions and can be eliminated. So that we bring back some of Unit 2 into this. To simplify things in writing redox equations in ionic form, chemists usually indicate hydrogen ions by H+, understanding that of course they're the hydronium ion. The equation can be written showing only the substance that undergo a change. So copper, yes, it doesn't occur on the right hand side, so we'll write it down. 4H pluses, yeah, it doesn't occur on the right hand side, so we'll write it down. 4 NO3s on the left, 2 NO3s on the right, so we'll cancel 2 on the right with 2 on the left. That leaves us with 2 on the left, and then copper 2 plus on the right, 2 NO2s on the right, and 2 H2O. So just crossing out the spectator ions. Now, if we look at it in unbalanced form, it's simply that. Okay. Yes, there are the questions we did. Also, you might even see this same reaction expressed in a way that shows only the substances that are oxidized and reduced. So if we just look at those ions that involve an element that is oxidized or reduced, we're going to shorten it just to keep that. So H will be a +1, H will be a +1. So we take a look at that. We could get rid of that. And then we look here, copper is going from 0 to +2. And nitrogen will be undergoing a change as well. So in this case, the hydrogen ion and water molecule are eliminated because neither is oxidized nor reduced. The H's and O's in there are not. There's no change that happens. The only additional information needed is that we need to know what type of reaction this is. It's either going to be an acidic solution, in which we have H pluses and water molecules in abundance, and can either appear as reactant or product, or whether it's a basic solution, in which we have an abundance of hydroxide ions and water ions, and of course they could occur on either side. When it's a basic solution, it's a little more tricky. You might have to be given a hint as to which side each of those will be on. So if you try to balance the equation above, you'll see that it appears impossible. Net ionic equations can still be balanced by applying the oxidation method we just looked at, and we'll go from there and see exactly how to do that. So if we look at this example here, use the oxidation reduction number, or the oxidation number method to balance this, and we're told it's in acidic solution. So we'll have H pluses on one side and water molecules on the other, whatever will seem to work out. So here, the key thing, of course, by balancing by oxidation numbers is we know that the increase of whatever is oxidized and reduced, it must equal out. So the number the increase of oxidation number must equal the decrease in reduction. So applying the oxidation numbers to this, it's kind of small here. They don't show the totals on the bottom, but you likely should. So plus 7 minus 2 minus 1 minus 1, 0. So we can see chlorine goes from plus 7 to negative 1. It's getting more negative, it's reduced. And to go from plus 7 to negative 1, that of course is a change of negative 8. Oxygen, don't have it on the right hand side. Bromine's going from negative 1 to 0, becoming positive, it's oxidized. And the difference to go from negative 1 to 0, that's plus 1. So as we can see, it's very similar to what we had before. We have to have these changes being equal, because what's losing electrons must be equal to what's gaining electrons with another substance. So multiply that by 8. So that implies we're going to have 8 bromides. So 8 bromides, and of course to make 8 bromides on the right, we put a 2 in front of there because it's diatomic. Okay, and as we can see here, chlorine, 1 chlorine, 8 bromides, but oxygen. We have an oxygen on this side and nothing on this side. So we have to add enough hydrogen ions and water molecules so that we can get enough oxygens on each side. Now there's a hint with this one. Since there aren't, it's an acid solution. So since we have no oxygens on the right, I mentioned a little note here, must add H2O on the right, since there are no oxygens on the right, to balance the oxygen atoms present in ClO4-. So that's kind of a little hint there. Sometimes it's obvious which side H plus should be on and which side water should be on, because they have to be on opposite sides. So that kind of gives you a little hint. Take a look at what you have and then go from there. So then doing that, let's see here, where was it done? Oh, right here on the bottom. So adding H2O, adding H pluses, balancing out the oxygens. So 4 oxygens, so I have to put a 4 in front of there. That's going to give me 8 hydrogens O, and the only hydrogens here are the H pluses that I've added, so right there. All right, I think we'll call it quits there. When we come back, we'll look at some examples here and then finish this up. Okay, we'll see you again.